Start record. Okay, so start record. So now we continue to the second part of chapter 3, which is later will be explained. Okay, so last week we have covered on the introduction and definition of Fourier transform. Okay, it's actually to transform the non-periodic to transfer non-periodic time domain signal to frequency domain signal. Okay, so okay, that's it. And then refer to your appendix. If anything, always refer to your appendix. So like this, I make it. Okay, so properties of Fourier transform that we will learn today, inshallah. Okay, in this 1 hour is about properties of Fourier transform, which is linearity and superposition. I think last time during in-class exercise, I did ask about linearity, right? Okay, linearity and superposition, time shifting, time scaling, duality, frequency shift. Frequency shift is actually a way of, one of the example is actually when we want to transmit our signal. Okay, we modulate the signal. For example, when you listen to radio, right? For example, Zayan FM. What is the frequency? 20 something, 28 or 23, I forget. Okay, Zayan FM. When you want to go to this, to tune to this radio, do you actually .fm, right? That is the modulated signal. Okay, modulated signal, communication signal. Information signal actually sometimes or most of the time is low frequency signal. Information signal, for example, audio signal. When you and I'm talking right now, okay, it's not really high frequency. So in order for it to be carried away over some distances, or for communication whatsoever, it need to be carried by a higher frequency. Okay, this higher frequency is, for example, the what that when you tune to radio, you see 23.8 FM. Okay, this is the actual frequency of the carrier wave. And then some brief about convolution, but for the frequency domain. Okay, because the assignment is on chapter 1 part 3, which is on the time domain. So this one convolution is different, this one is frequency domain. And then differentiation. Okay, so go to the linearity and superposition. Okay, if the concept linearity is actually, I told you guys last time, what is actually if you attend the in-class exercise, or I'm not in class exercise, if I know a second. Linearity is that any similar changes that you have in your input, you're going to have that similar changes in your output, something like that. Okay, and then superposition is that when it's the effect is like superimposed, like add summation of that effect, something like that, combining. Okay, so if v1 is equals to v1 in frequency domain, v2 is in v2 frequency domain, then if it's linear and superposition, the system should be like a v1 plus b v2. In frequency domain also will cause a v1 and b v2. Okay, same amplitude scaling will also occur in the frequency domain as well. And if it's linear, it is undergo the similar changes. Okay, for example like this, a b. So you can see this is actually this one you can get from your appendix. Okay, they use small b here. It's okay, it's just coefficient. Okay, they use in table C. So you always need to refer to the appendix. Okay, if I know for a second, for this Fourier transform, okay, because I said them check this one. Okay, it's table C, C.1, C.2, C.2b. Okay, and Laplace is different chapters. Okay, so you see here, find the Fourier transform for signal GT as shown below. Okay, Fourier transform means it is a time domain, but we're going to have a frequency domain as our signal. First, what we actually need to do, okay, we see this, you already see this, what you call this table, okay, in C.1, if I'm not mistaken. Okay, And then later on you see from C.2A or C.2B, do you see any similar signal? Okay, so you can see here this is actually the signal that given as GT, and you can see this, there is no such shape inside this table, right? Directly you see there's no shape, but actually it actually consists of two rectangular wave. Am I correct? Two rectangular waves which is combined to order to have them. Okay. Some error happen, but you know this one is rectangular, okay? You know this one is rectangular. This is -1, this is 1, okay? So solution synergicity can be produced by using superposition, okay, between two signal. If you see here is -3 and 3, can if and then is related with the tau here is actually tau over 2 equals to 3, right? Tau over 2 equals to 3 is, and for this particular G1T, tau is actually 6, okay? And this one is tau over 2, okay? Tau 2 because it's synergy 2. Tau 2 over 2 is h equals to 1. So t equals to 1 times 2, which is 2. I think you guys familiar already where is the pin. Okay, 3 and 3. So you guys know, right? Tau over 2 based on the formula here. Okay. So we put tau 1 because it's G signal of G1 and actually equals to 3. So you know tau 1 is equals to 6. Okay. So here you can see, right? Okay, you can see that the resultant is actually for the individual is actually A tau sinc omega tau over 2. Okay, so you can see this one, the A is 0.5, this one the A is equals to 1. A1 equals to 0.5, A2 equals to G2, equals to 1. Okay, so here that's why you have A 0.5 tau T over 6. Okay, T over 6, and omega tau over. Okay. Okay. And then G2 equals to rect T over 2. Okay. Rectangular T over 2. And from table C.2, okay, from table C.2, you know that actually A rectangular T over tau is actually A tau sin omega T over 2. Okay. So you just substitute, you just make a comparison. Okay. Rectangular is equals to sin, for example here. Okay. And then the second pair is rectangular. Wait. Okay. So the next pair is this one. Rect t over 2 is actually the second pair. Okay. You make like this. And then because of it is linearity and superposition. Okay. GT is actually equals to G1T plus G2T. Okay. G omega G1 plus G2 omega. So we get the answer 3 sin 3 omega 2 sin omega. You can rearrange this one to your convenience, or maybe for better, let's say the question asks for you to, to sketch. So this one put in front, because this one is 2 sin omega, omega, and then here put as the second one because this one is 3 omega. Okay, put in order. Otherwise, if they don't, just to avoid you to make mistake for sketching. So the next is actually the properties of the time shifting. Okay, I think this one is not in your table. Okay, that's why always I ask you to see your appendix. Okay, because this one I crop myself. I put here. Okay. Otherwise, when I'm teaching, I keep on referring to appendix. It will be inconvenience to me and will be inconvenience to you. So that's why I crop and I put here. Easy for me to refer. Okay. Time shifting is time delay of signal cause a linear phase shift in the spectrum of the signal. So if the signal is delayed by T0, the phase spectrum will be shifted by negative omega T0. Okay. So normally, okay, let's say we have a signal which is delay by t over t naught, delay by t naught, and let's say the signal is f, okay, and then in the time domain, in the frequency domain, okay, the same delay will actually be represented as this one, e negative j omega t naught, okay, e negative j omega t naught, okay, this is the delay. Okay, there will be no changes in the magnitude. Yes, correct. There's no changes because this is about, there's no changes in magnitude because this is about time shift. Okay, so if the signal is delayed, the phase spectrum will shift by negative omega t naught. Okay, this is just frequency. Frequency. Okay, so you can refer to your to here. Okay, the writing. Okay, here find the Fourier transform for signal 3e negative 2t minus 0.5. Okay, um, okay, how I'm going to change this. Don't feel like, oh, that is test question. No, that is not test question, right? That is past test question. The one that you saw just now. Okay. Wait, I'm reordering my screen. Okay, time shifting. Okay, so I just I won't do until the end, otherwise it will take some time just to cover all of the operation. So refer to your slide number 8. So this is a signal given like 3. Okay, 3e negative 2 t minus 0.5. Okay, is it clear? I hope it's clear. Okay, so 2t minus 0.5. You can see this one doesn't, if you see directly, of course, you see like no such thing inside the table. You need to always relate with the basic, what appendix can give you. Okay, so what is actually the appendix give you is actually, if we refer to table C point, which one? Wait, so it's a time shifting. Refer to appendix with a time shifting. Time shifting. Okay, time shifting. So which page of time shifting? Table C.1. Okay, buka Laplace pula, salah. Okay, same time shifting. So before we see this, okay, before we see this, you know that time shifting is actually f t minus t naught is equals to not equals, is something like this, to show that it's frequency domain. So f big one and omega and c and the shifting. Okay, t naught. Okay, and then you refer to the shape, to the signal that is given is actually the in terms of exponent. Okay, exponent. So this one is actually, if you see, if you want to put the standard one, is 3e negative 2 over t. Okay, something like this, the basic one. Okay, and then you have actually see that it is shifted by this. When you later on expert, no need to do like this, and this is just one for me to teach you guys so that you understand. Okay, so it's delayed by 0.5. Okay, the real one, the standard one, from the table. Okay, so a e negative what is it, at Fourier transform. Okay, a plus j omega plus a. Okay, sorry, out of order, later on you guys confused. A plus j omega. Okay, so a plus j omega. What is the difference? Oh, okay, so a plus j omega. So you know your a here is actually 3. Okay, this is actually 3, and e is what? E is negative 2. A is negative 2. Okay, and t. Okay, then you have your actually 3 2 plus j omega. Okay, before the shifting. Okay, before the shifting. So when you have the shifting, actually you just need to do is there any I missed something? A plus j omega, any different. Okay, a plus j omega. Te from the table. Wait, I think I'm missing something here. Oh, okay. It's not I'm missing something. I forget there is modulus. So I forget there is modulus. So actually we have modulus is actually the signal is always positive. Okay, so this is the table. Okay, and the graph, and forget this one. Okay, no wonder I feel a little bit weird. Okay, so refer to the table. So this one is actually the signal before a e negative a modulus t Fourier transform. Okay, and you have 2a over a square plus the omega square. Okay, this one is the small a. So you know your a here is given, a is actually 3. Okay, 3, and small a is actually, what is a small a? Small a is 2. Okay, over a is actually, a is given as 2 square plus omega square. Okay, so this is before the shifting. Okay, then you need to introduce the shifting. Okay, you need to introduce the shifting. You just provide this one, 2 times 3, 6, 3 times 3, 12. Okay, 12, and then 2 square is 4 plus omega square, and then you just need to provide e negative j omega. Okay, t naught. Sesama. Okay, t naught. So what is your t naught? T naught is half. Okay, t naught is half. You can see, right? The t naught is half. So that's why t naught half. So that's why it's half here. Okay, so you make simplification is j omega over 2. Okay, so I think it's quite simple. Okay, so you can see the example. You can see the example, and then you just do accordingly the sketching. Okay, you can see this one is always positive, so that's why modulus. This is what find time shifting for transfer signal. Find the for pulse. Okay, this one is also shifting. You can do at your own. Okay, you can do in your own. You know this one is actually shifting by half, right? You try test yourself, huh? Okay, because the standard rectangular tau over 2, tau over 2. Okay, now it is shifted. Is okay shifted to tau. The width is still the same. Okay, the width is still the same. So the only changes it is shifted to the right, and however the width is still the same, and also the amplitude still the same. Okay, you guys can try at home. Okay. Example 4. Oh, okay. There's a solution. Just try it at home, okay? And check your own answer. Next is time scaling, okay? Okay, it's a bit, you can read yourself. If A greater than 1, signal will compress. Okay, you guys can read this. Maybe I will explain a bit more simpler. Okay, if actually you have A, there is condition whether A is actually greater or less than 1. Okay, if your A is greater than 1, means the signal in the time domain first. Okay. Okay, we have condition A greater than 1, A less than 1, and A greater than 1. Okay, we have these two conditions. Okay, so if it's in the time domain and is in the frequency domain. Okay, so if it's this in terms of scaling, so if A greater than less than 1, mean what happened to the signal? Signal will be compressed. Okay, maybe I create a graph so that it will look more. You guys can imagine. Okay, so if A is less than T, okay, less than 1, for example, you have A equals to half, for example. Okay, so your signal will be, your signal in time domain will be expand. Okay, what is this? Okay, for example, this one. For example, signal will be expand, for example, 3. Okay, and then however, it will be compressed. Okay, it will be compressed in your frequency domain, become more slimmer. Okay, let's say now you have A greater than 1. If A greater than 1, mean your signal is compressed. Compressed, for example, 0.5. Okay, and then however in the frequency domain, okay, in the frequency domain it will expand. Okay, something like that. Okay. So example, rectangular signal T over tau. Okay, T over tau V omega. This is the standard one. Okay. Is there any example? Okay, example. Okay. So if V1 equals to V to T, okay, you can see the V to T. This is a time scaling. Time scaling. Then you will see actually go to the formula in the table. Nampak ni. Okay. Sorry over pula besar. Okay. So time scaling, you see your A here. So 1 over A, 1 over 2, and omega over 2. Okay. So therefore, that's why if you have V1 equals to V to T, the rectangle is 2T over tau. Then then in the frequency domain is 1/2. Okay, 1/2 because time scaling is 2, and then wait ah sesama. Okay, so 80 sin omega t over 4. Okay, because the initial equation without the time scaling is already divided by 2. Now we divide again by 2. That's why is we have division by 4. Always refer to your table for to see the shape the shape of the signal and properties. This one is rectangular, and you know when rectangular we want to change to our frequency counterpart is actually we're going to get sync signal. Okay, and sync signal is here. This rectangular. Oh. Why I keep on looking at Laplace transform? It seems like I'm so excited to teach the next subject. The next chapter. Okay, rectangular, you see here is omega t over 2. So then you divide by another 2. That's why you're going to have omega tau over 4. Okay, but there is no changes in the time shift. Okay, there is no changes in the time shift. So tau is actually equals to 1 there. Okay, is it equals to 1? Okay, tau over 2. Okay, depends on what the signal that you actually have is tau over 2. It means is if it doesn't change, it's tau over 2. Okay. So here, okay, this is your signal. Okay. I think I already demonstrated just now the changes. Okay. So you guys can try at home. Okay. The concept actually to see the signal become much more slimmer. Okay. Mm, I did try here. Okay. What is this? So a rectangular tau over t over tau. Okay. So this is actually the signal, the standard one. Okay, the standard one. And then when you do the expansion, okay, when you do the time scaling, okay, time scaling, whether it is going to be smaller or going to be expand, you need to look at the A. Okay, you need to look at the A. This one is example rectangular. You can get different kind of question. For example, this one. Okay, you can get this one. Okay, so what you need to do, okay, you just change accordingly inside. Okay, you need to know the A first, and then you change accordingly. Okay, the scaling. Press the pen. Okay. Okay, is 1 over A F omega over. Okay, you see here. Okay, you get this from your table. So it's omega over A. Okay, if it's being scaled, okay, being time scaled by A. So if whatever function that you have, whether it is going to be seeing from, because rectangular will get seeing and so on, triangular will get what you see from the table. If the table didn't give you, you need to differentiate or you need to do yourself. Okay, hopefully you don't need to do yourself, just refer to the table. Okay, so you have a signal which is you going to have 1 over A, and then this is the Fourier, right? Fourier transform means if you're given your signal is given by sync by rectangular in time domain, in the frequency domain it will be sync signal. Okay, so here will be function of sync signal. Okay, and with the changes of omega over A inside. Okay, that's why from the slide, from the question, you, Where is the question? Okay. This so you see, there will be like omega t. There will be changes inside. Okay, but the function is still the same. The function is still sync. Okay, because that is the output frequency transform in terms of sync signal. Okay. Time inversion. Okay, time inversion is actually just time reversal. Okay, time reversal. The same, this different. I mean, the thing is the same. The name time reverse time inversion is still the same. So if, for example, if you have 3e, wait, where's the table? How I'm going to divide the screen? Oh, too small. Okay, so time reversal in time domain is given for f. I think you familiar with this. In chapter 1 we already done. Okay, so we time reverse. Okay, and it, actually for our Fourier transform, we're going to have that signal. However, in its frequency domain, it is like this. Okay, so reverse in frequency domain signal. Okay, so the example given. Find the Fourier transform for signal 3e. Sorry, time inversion. Okay, so find the Fourier transform for signal 3e. 3e negative 2t. Okay. So you see from your table, okay, you see from the table where actually you can get this from the table, okay, given that this exponent. So that we see from the appendix, okay, that we see from our appendix. Okay, so blah blah blah. Okay, so which actually the signal that you have uh, which signal is actually familiar. So it's either decreasing exponential function or symmetrical decreasing exponent function. So you need to see the difference. You need to see the question. Which is the question? So negative 2t. Okay, I think this one I take it wrongly. Okay, night time. So find the Fourier transform for the signal. So you have 2AA over omega square plus omega square. This one is about time inversion. Time inversion. Wait, I want to check something first. Because why the question is yeah, it's decreasing. This actually this one. This I think this is this guy. Ignore this one first. Ignore this one first. Later I check. When you get the flu, your brain not really working. Okay, morning. Okay. Uh, wait. Later I go to that back. Okay. So duality is okay. The next step, the next operation is duality. Okay, duality is actually signal. You have in, for example, you have similar shape in frequency domain. However, that signal is actually initially is meant, for example, the characteristic of your time domain. Okay, for example, For example, when you know it, when you solve rectangular, you will get sinc function, right? Okay, which is in in frequency domain. The case that we consider duality is that we have the same signal, but it is in time domain. Okay, you see here. So this is concept. That's why this concept that we actually call it as a duality. Okay, duality. So if it's duality, we can do some. We can do simplification, or you don't need to. You just need to. Vt is omega. If it's Vt going to be transformed to your time domain, to frequency domain, you just need to add 2 pi and you're going to inverse the frequency domain. So the duality of signal means that frequency spectrum for Vt will has the same form as time domain signal but having inverse operation of frequency and amplitude scaling of 2 pi. Useful to obtain Fourier transform for time domain signal which have the same. Okay, you can read this later on to yourself. So this one is find the Fourier transform for the signal. Okay. Okay, you see here. Okay, where's the pen? Okay, wait. I'm adjusting my screen. Where's the question? So you see, the question is giving you GT equals to A tau, okay, and sync T tau over 2, okay. So this one is actually initially is actually in your time domain, in frequency domain, right? So now you have it, but this shape signal, but it is in the time domain, okay. So normally the initial one, where is the signal? Okay, the initial one you have A rectangular T over tau. Okay, when we want to do Fourier transform, we will have A tau sin omega tau over 2. Okay, look to your table. Okay, now instead you have this same signal, but however in the time domain, which is this one. Okay, okay, so how are you going to obtain your what's called Fourier transform? Okay, the Fourier component. So it's actually what they call just now. Okay, what is the example gave just now? Duality. Okay, so it's actually 2 pi. Okay, 2 pi, and then it's G, big G, and then inside with negative omega. Okay, so now you just do accordingly. Okay, you just put inside. Okay, because this one is rectangular, to you will get sync. Now sync in time domain you get rectangular. Okay, terbalik lah macam ni. Okay, the shape I'm not talking about I'm talking about the shape the shape of the signal. Okay, almost equivalent. So this one is actually in your rectangular. So 2 pi. Okay, so refer to your rectangular equation, rectangular. Okay, and then you will have what here? Negative omega. Okay, you see here, this one is tau, but it's become negative omega because the definition says so, right? Negative. And then you have tau. Okay. Okay. Okay, so actually if you going to draw your rectangular graph, okay, you will get actually rectangular, right? Rectangular signal with negative tau over 2. Okay, this is the standard based on the table. Okay, and your amplitude will be 2 pi a. Okay, because following this. Because this signal is actually duality, because you see it is symmetry. Okay, it is symmetry. So negative omega can be treated like omega. Okay, because it's symmetry, 2 pi a rectangular omega over tau. Okay, so this is your g omega. Okay, so this is your g omega. Okay, the whole of this. Okay, so you can see, right, this first you have rectangular, then in frequency domain you have sin. In time now, for duality is that you have sin, but in time domain, then you're going to have the corresponding frequency domain in rectangular. Okay. We start at 9:30. Maybe I will ask you to guys to rest. Give you some time to rest. At 9:40 as well. Okay, 9:40, because we start at 9:40. We start at 8:40. Okay. 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 Where were we? So I put into my slide, but you have to write on your slide somewhere, because it's already given to you, the slide before the class. Okay. Next, find the Fourier transform. Okay. Oh, okay. It's given. Okay, it's given, so you guys can see yourself. Okay, because I already explained. Okay. Now, frequency shifting is what I explained just now. Okay. So frequency shifting is actually for us to carry the signals. Okay, so it will be carried by a higher frequency. Okay, I'm not sure if you guys study or not principle of communication. Okay, you will study this inside subject called principal communication, about modulation and everything. This one is about principal communication. So you need to pass this subject. Okay, you need to pass this subject. If I know a second, before you going to get the next one. The next one is principal communication. Okay, means prerequisite for principal communication is I think is signal. I'm not sure. Okay, that's why I'm looking. Even now I'm okay. Internet slow. Okay, never mind. Nothing we can do if internet is slow, right? I just want to tell you, to show you something. You see? Okay. So you see here, this is the signal. Okay, your information. We can call it information signal, audio signal, whatever. Is actually signal containing information. Okay, so they can call whatever they want, audio signal, TV signal, whatever. Okay, but it's signal containing information. So you need to carry it by higher frequency wave. Okay, higher wave to carry the signal over distances. So this is the carrier wave. Okay, you can see carrier wave. For example, you can have carrier wave in cos omega t, higher frequency, or you can have sin omega t, or you can have other. Okay, and then this one, here modulation show that ft, the information signal, okay, times with your exponent negative j omega naught t. Okay, this is the carrier wave, and you're going to have frequency in frequency domain as f omega minus omega naught. Okay, for the cos and sine, you will have the half of them. Okay, means half, and then your frequency will be plus by omega naught, means this one will be advanced by omega naught, and the other pair is will be delayed by omega naught. Okay, and this one is 1 over 2j. Why 2j? Because you know, right, from your evilus. Okay, sin is 2j. We have 2j at the bottom part. Okay, and then omega minus omega naught and omega plus omega naught. Okay. Oh, okay, it's given here. Okay. So example 6, find the Fourier transform for signal. Okay, given the signal is g f t cos omega cos 20t. Okay, where ft is actually 2 rec t. Okay. Okay, I want to ask you guys. New. Okay, when split screen again. Oh, okay. So I want to ask you why that question. Refer to that question. Why our GT? Okay, why our GT is not continuous? Why our GT is not continuous? I mean, why is not continuous? Why is only like this? Ignore my drawing. Terrible drawing. Okay. Why is only stuck at 1 and negative 1? Can you guys respond? You go check why. Why our GT is like that? Should be in the first place, it should be continuous, right? Continuous cos signal. Continuous something. Why GT is only why GT only stop at 1 here and 1 here? This is your time domain signal. Okay. Why? See the slide and try to give answer. Why your GT is actually is not over all the time ranges? Why we only have until 1 and 1? Why we only have here? Try to answer. Try to answer why we only have GT is actually just a portion, okay, of not continuous. You guys know not? No one answering me. Do you guys all know why this one is not continuous? Why GT is start from negative 1 until 1 only? Refer to the slide. Why? The answer is already there, but I just want you to know you know or not, because you know question exam can be different thing. So if you don't understand I mean what is going on, okay? Why GT the signal, okay, given that GFT cos omega naught t, where ft equals to 2 rectangular t, why you only have GT just a portion, it's not over all the axis? Why it's not continuous like this? Why it's like this? I give 1 minute. What do you think before I give answer? Try guess, because you know exam no time guess. Okay, thank you. No Aisha Amira. How about the others? Only no Aisha Amira in my class. Where is the other student? I think in my class there is 30 plus. So, but only one answer. The rest is doing what in the class? Okay, I cannot wait. So, thank you, Noaisha Amira, for to actually respond to my question. It's the important thing is you have the guts to respond. Okay, right or wrong is different thing. Okay, we are learning. Okay, we are learning. So if you don't learn, if you don't try to, I don't know. It's depend. I think you know already. Okay, I don't want to repeat things macam mak nenek pula. Okay, so why? Because the function here is ft is actually rectangular because it is rectangular. So you see rectangular, so means it is only certain ranges. Okay, that's why it is cut off from -1 to 1. Okay, you need to see the rectangular function. Okay, so you see here is tau over 2, and then you you match the two rectangular, okay, with the cos. Okay, so that's why you have your cos like this, the initial cos, but however it is only cut according to the uh, ranges of the what do you call it, the carrier wave. Okay, we call it as a carrier wave. Okay, so you see here f omega 2 sin omega over 2. Okay, solution 2 sin omega over 2 because we have rectangular, right? Rectangular times cos. Okay, we have the in terms of sin function for the frequency domain because this is a rectangular. Okay, rectangular. Maybe I just show. Okay. Okay, this is just not related with that question. For example, you have your rectangular, and then you have the cos signal. Okay, and then you multiply them. Okay, I mean you modulate them together. That's why it's only this one is only taking the certain range inside. Put different color so that easy to see. Here, for example, okay, only this area. So that's why it's being cut. Okay, instead of having continuous, you only have this one, following the width, the range, okay, given by the rectangular signal. Okay, initially it is continuous, right? The cos, okay, because there is the cos. Because after moderation, the information is only at specific time, and there's no other information at the missing modulated signal. Okay. This one is actually the time. Okay, the time when we multiply means this. It will follow because the initial equation is rectangular. Okay, you see the ft, the information signal is rectangular, and the carrier is cos 20t. Okay, cos 20t. So means the information is limit the range of this signal. Okay, following the rectangular. Okay, otherwise it's like continuous. Okay, so g omega, so you do it accordingly. You see f omega minus 20. Okay, because it shows here is the carrier wave omega. Where is the slide just now? You see here, you can see here j omega naught t. Okay, and then you can see if it's in cos omega naught t, and sin omega naught t. So cos omega, our question is about cos omega naught t. So omega naught is actually 20. So this is W minus omega naught. So W minus 20. W plus omega naught. So W plus 20. Okay. And you know actually the signal is actually rectangular, right? The rectangular for GT. Total of them is rectangular. So that's why you have sin in terms of sin function. Okay, sin function, and you sin omega minus 20 over 2, omega plus 20 over 2. Why? you see is provide here, right? Okay, provide here, divide by 2, okay. Divide by 2 by here, the amplitude, okay. But here you can see this one divide by 2 is from the table, okay, from the table here. So you can see it will be a smaller sync signal, okay, by half, okay, by half, because when we do the modulation. So you have the, when you do modulation, where is this snipping? This one I shouldn't explain now, but never mind. Because you will learn later on. You don't need to learn now. Okay, where so you can see when we modulate, we have the higher wave and the lower frequency wave. Okay, so this one is this one is actually, you can actually know this one is the result of this, right? And this one is actually the result of delay. Okay, but this is your higher frequency wave. Okay, when we do modulation, for example, if our signal is 2 hertz, for example, our signal is 2 hertz, very low frequency, but our carrier wave, for example, 2 megahertz. Okay, 2 megahertz. So if you see 2 megahertz and one is 2 megahertz and 2 hertz, we is this one will be like negligible, you know. So this one will be following the higher frequency. So 2.000 something megahertz here, and the minus will be here. 2 megahertz minus 2 hertz is here. Okay, information signal usually lower frequency, so it cannot go to, you know, cover wide distances. Like you talking, your friend at the eon cannot listen to your voice, so you need to modulate. Okay, this one ignore this one, you guys. Okay, convolution. Okay, convolution, previously you learned about convolution, but for group assignment you will learn. Okay, you will learn. So convolution is actually here. Okay, convolution is the interaction between input xt and impulse response ht. Okay, so this is your output. Okay, this is your output and this is your input and this is your LTI system. What is LTI here? Do you guys know what is LTI here? LTI system, do you guys know or not? What is LTI? You guys know or not what is LTI? Later in test or final you mention LTI, you don't know what is LTI. Do you guys know what is LTI? Okay, good. It's linear time invariant. So what is linear time invariant? It's a fixed system. If you provide in system is t minus 1 in time domain, in frequency domain should have similar changes as well. If t minus 1 in time domain result in frequency domain, for example, t minus 4. Okay, initially is t minus 1 in time domain, but in frequency domain it become omega minus 4, for example. So it is not, it's a varying system. It is time invariant system if the same changes in input will translate to the same changes in output. If t minus 1, it become, for example, omega minus 1. Okay, something like that. Okay, something like that. Convolution is the interaction between the input signal and the impulse response. Okay, you can see this is your impulse signal xt, this is your transformer. Okay, they can call whatever, impulse response, whatever. Okay, but this is like just like transformer. Okay, the general name. Okay, I call it transformer. It's still correct. Okay, so ht and output signal. So this going to transform your signal. Okay, transform your signal input to become an output. So what happened is actually your input will be convolved. Okay, convolve with your ht. They will convolve together to produce yt. Okay, in time domain, the convolution is actually integration from negative infinity until infinity, and you have x tau, your signal. Okay, x tau, h tau minus t, and then you will integrate with respect to tau. Okay, and then But however, in frequency domain, it is easier. Okay, that's why it is easier, because in frequency domain, if you have convolution, okay, if you using frequency domain, if you convert this one to frequency, this one is to frequency, this one is to frequency, this is actually the convolution is just actually the multiplication. So x omega times h omega to get y omega. Simple, right? If not, you have to integrate in time domain. So you can see here, okay? You can see here V1 convert V2. You get in frequency domain is just a multiplication. Otherwise, in time domain, you have to integrate, okay? So your group assignment later, you perform this integration, okay, in time domain. Okay, I give you 10 minutes. We will continue at 9:55, okay? You can go take whatever you want, okay? We rest for a while. Okay, we continue our discussion. Okay, so this is the advantage of having convolution. Okay, convolution. So you can see the signal. If it's convolved in time domain, you need to do integration. However, if it's in frequency domain, it's just simply a multiplication. Okay, so you can see here, this one is the F1t convolved with F2. You're going to have F1, F2 omega. Okay, and this one is actually F1 times F2t. You get 1 over 2 pi over F1 and omega and F omega. Do you know? Okay, you tell me later on. Okay. You see here, this one is F1 convolve F2t, then you obtain F1 omega, F1 omega times F1 F2 omega in frequency domain. And then why we have here F1t times F2t, we're going to have 1 over 2 pi convolve. Now, why the frequency domain is convolve? Okay, this one is shown to you in the previous previous properties just now. Okay, so I need you guys to hopefully you guys can relate why this second part we have F1 times F2t, then will result in convolution in the frequency domain. Okay, I will not ask now. You need to maybe browse your slide later on. Actually, there is already shown there. Okay, given two signal as below, you see F1t negative A ut, A greater than 0. Okay, and then F2t negative B t ut. So you can see this is actually related to this signal. Ayo, wait. Okay, so easier for me to conteng. So, okay, you see this one, you just need, you relate to your table. First, you need to refer to your table C.1, for example, C.1, and then you refer to the other table, which is, I think, C.2b. Okay, I mean C.2, okay, and then you can see which signals related to it. So you given that F1 is negative A minus AT, a unit step. Okay, when you have unit step is what? You only have value at the positive region without time shift if there is no any shifting. So you only have for value 1 at the positive region and the rest will be 0. So that's why it is we only have value for greater than 0. Okay, for greater than 0 because the unit step function. We already cancel anything here. We don't have any function because everything times 0 will get 0, right? Okay, the same goes for your F2. Okay, so if you want to obtain the FT, for example, your output, okay, your output is actually F1, for example, input convolve with the transformer or convolve with the impulse response, whatever the name they give. I think impulse response, where is the name they give? Just the same, okay, impulse response hash is just the same. Okay, okay, and then you do the convolution. Okay, with this one you will learn during your group assignments. You will learn to group assignment using MATLAB to obtain the convolution to perform convolution. Okay, in time domain. Don't give me in frequency domain, but never mind, later on I will give the group task, then maybe you will understand. Okay, so then convert to your frequency domain. Okay, so it is just multiplication. Easy, right? In frequency domain. So you know this one E matrix AT is actually result in this type of frequency domain signals. Okay, so you just add accordingly, and it is multiplication because convolution, convolve in time domain will result in multiplication in frequency domain. Multiplication. Okay, so then you do this one is just mathematics. Okay, this one is also mathematics. Okay, in the end you get this answer. Okay. See carefully, this one is FT in time domain. Okay, this one is in frequency domain. Okay, next. Is this given inside or this one is the one I'm chanting? Okay. Okay, differentiation. Okay. You guys can try it at home. This one just now because it is there already. Okay, solution. You guys can try. Okay. And then differentiation. Okay, differentiation. So differentiation, refer to your table. Okay, refer to your table. You can see here actually given like dn means you can differentiate for more than one. For example, first differentiation d dt, second differentiation d square dt, third differentiation d3 over dt, d to the power 3 over t. I think you guys understand. So that's why we have here dn. Okay, means it can depends on how the order of differentiation. Okay, and then the order of differentiation will result in if you're going to transform it, it's actually j omega to the power of n. Okay, so if you just first order, so this is j omega, but if second order, j omega all of them will be squared. Okay, will be squared with f omega. So and then the below part. Okay, you will see later in table will be more clear. I'm not sure if this my slide is clear to you. Okay, but if you want to have a clear view, you go to your appendix. Okay, so given here. Okay, so you see the example. Is this example you guys have it or not? The example, I think you guys have. I hope you guys have, or you guys don't have. Okay, so this one is actually a triangular signal. Okay, triangular signal consists of wait. Okay, so this one is triangular signal. Okay, triangular signal. Wait. Okay, so you can see we have portions. We have portion. Which one? Wait. How to highlight? Okay, highlight. Okay, we have this portion, which is the positive, positive gradient, and then we have this one is negative gradient. You know, right? This one is just like your what we call it. What we call it? First, you know, gradient. Okay, y plus c. Okay, so this one is actually for this part. Okay, for this part, you have what is the equation? So the intersect is actually a. Okay, and then what is your gradient? Okay, gradient, for example, 80. Okay, and then the second part is negative, right? So you have negative 80 plus a. Okay, because this one is, so this is you know, the triangle, and then you differentiate. Okay, if you differentiate, you will lose this one, right? Because this is constant. You will have this one instead. T is gone, you have a. So you have constant now if you differentiate by first order. Okay, First constant is a second constant is negative a. Okay, this one just now is like a plus. Huh? These two guys. Okay, this one plus with this one. Okay, so now you have a and you have negative a. And if you want to differentiate again, okay, differentiate again because now it's number, right? Now it's number. When you differentiate again, you will lose. It will become just like an impulse. Okay, just like an impulse. So the first order of differentiation dgt over dt. Then you have actually the in terms of a rectangular 0.5. Okay, and minus a rectangular negative 0.5. Okay, and then if you do the second order, it will become impulse response. You can see here. Okay, okay, so they explain here. Okay, a rectangular minus a rectangular is negative 0.5. And then j omega, you see first order variation, you use first order here. So first order d vt over dt j omega d omega, n is equals to 1. Okay, so that's why you only have j omega here. Okay, and you know rectangular is actually like this, and there is any shift, you just couple with e j omega over 2. I mean, it depends on what shifting. Okay, if, this one is 0.5, this one you have j omega over 2. This one is this one is advanced 0.5, so you put j omega ni. Okay, it's not advanced, it's like delay delay to the right. Okay, delay to the right. This one is advanced to the left. Okay, then you perform, this one is actually minus. If you see, actually they are the same async omega naught. This one is the same, and this one is the one that is different. Okay, so you do j omega. Okay, because this one you put on the right side of the equation. Then you do the mathematics. Okay, you do the mathematics j omega. You can bring them up. Okay, and then you have 2 here. Okay, so in the end, you will have async square omega over 2. Okay. Next is actually the second order differentiation. Okay. Second order the same, but however, it will give to a difference in this. Okay. D square Vt dt square g omega square. Now it's square. So j is equals to what? Do you guys know j is equals to what? J is equal to what? Do you guys remember? J is equals to what? Do you guys remember j is equals to what? How? Yeah, yes, imagine number, but j is equals to what? If you want to convert, I mean the value of the j. J, yes, it is imaginary, but if you have j like this, right? This equation, you have j omega square. What happened to the j if we square it? Yes, no, actually, I'm right, but if we square it, what will come? Okay, now you get the idea. Because I want to you guys to to try to think, because in so that you will use this. Okay, square. So you can decide. Depending on the question. If they ask you to do first order or second order, okay. I think it's a bit easier if they ask you second order, because you will square it. Otherwise, you need to do blah blah blah. Divide by j omega, divide by j omega. Okay. Otherwise, it's just like divide by omega square. You see here? Just divide by omega square. I think it's easier to say for second order. Okay. This is easier for second order. Okay. This one is just now. I think this one is wrong. Okay. So you do the time inversion. Okay. this f minus t. Okay, do you guys have the tutorial? Did I give you tutorial? Tutorial. Did I give you tutorial 3? I mean, wait, where is the tutorial? This one. This is no, this is tutorial 3. Tutorial 1. Okay. Tutorial 3, do they have the time version? Oh, only this tutorial. In ideal filter, block diagram which seems to be an LCI system shown in figure Q4, the filter. When because I want to ask you guys to do tutorial before because we have in class exercise right this week. Maybe later on I will ask you guys to do number 2. Obtain the Fourier transform for okay. This one is easy. You do the. You can if it's given in the table, you can use the table to obtain this shape. If not, you can do yourself. Okay. I think this is quite straightforward for this one. For example, how you obtain triangular. You should know. How you obtain RAM signal. For example, this one is just like maybe like a RAM. For example, how you going to obtain this one? Okay. First, you have this side, and second, you have this side. So how you obtain this one, for example? Okay. Maybe first is actually like this. Okay. And then in order to only have the positive one and the rest will be 0, you need to times with unit step. You need to time with unit step. Okay. Then you will have only, then you have the resulted signal. Which is only this one. Okay. So now you have this one, then this one is another process, just the same, okay? But now your unit step will be inverse, maybe. So your unit step will be inverse, okay? For this one, okay? I think I will ask you to do, you guys to do before the class, before the next in-class exercise, to do question number 2, number 3, and then number 4 is what? Determine and plot the output of the mixture, determination of filter transformation, oscillator in order to obtain the filters in plot the. Okay, maybe I will ask you guys to do 2 and 3 first. Only 2 and 3. Number 4 is maybe chapter 3, part 3. I'm not sure. Later I need to see. Okay. So you can see there is maybe inversion inside here. Okay, there is inversion inside. Okay. So you guys can practice. Okay, you guys can use this also. Okay. With that, we finish our class. Okay, we finish our class a bit fast, but please do the tutorial. Please do. Maybe you can use your time now. Actually, you have another. Oh, you have another 50 minutes. Not enough. Okay, go to your e-learning. Okay, go to your e-learning. Tell me what you learn. This one also good for me to see what have you learned. Whether you are dreaming in my class or you are not. Just be honest what you do. You don't need to write so long. You just need to write whatever you think that interesting or whatever you think that is significant. For example, where's your class? The class link. Or this one. Okay. For example, okay. For example, Aisyah Amira. Okay. Today, I learned that signal convolution in time domain resulted or produce, okay, produces signal multiplication of signal in frequency domain. That's all. If you smart or you have hardworking writing, and you can put whatever diagram you want. But this one is actually just what I want. Okay, then you just post to forum. Okay, and then later on when I see actually student have respond, then I will share the live lecture. I think I forget to share live lecture chapter 3 part chapter 3 part 1. Later I will share chapter 3 part 1, but section 4 lecture. Okay, because there is a error with your previous week lecture, chapter 3 part 1. So go to here and just start posting because you have another 15 minutes before the class finish. Okay, maybe you guys can do now. I can see, but then you can leave. You can leave the class. Okay, I will go to your e-learning. You just say what you learn. Okay. We have another 14 minutes. I also will have another class, Okay. I stop recording, but you guys can start